Muito boa tarde, sejam todos bem-vindos a mais uma sessão do mês da Ciência e da Educação da Fundação Francisco Manuel dos Santos. Desta vez estamos no Oceanário de Lisboa, estamos muito gratos ao Oceanário por todas as facilidades que nos deram para estar aqui hoje. Esta é a terceira sessão do ciclo, tem a informação lá fora, esperemos que continuem a acompanhar este mês de Educação e Ciência. Já tivemos uma sessão sobre a inovação nas escolas, em Lisboa, e tivemos outra sessão em Viseu sobre ciência e pseudociência, com Ben Golder, que é um médico que, enfim, tem uma grande intervenção nesta questão da diferença entre ciência e pseudociência. Hoje é a terceira sessão do mês, e eu peço-vos para continuarem atentos, digamos, ao resto do mês, que ainda agora está no início. Vamos ter a 14 de novembro, em Aveiro, na Universidade de Aveiro, uma sessão com cientistas portugueses que estão no estrangeiro, que vêm falar sobre os humanos do futuro, avanços em biomedicina que vão ter impacto nas nossas vidas. Nós chamamos cientistas GPS porque a Fundação Francisco Manuel dos Santos tem uma rede chamada Global Portuguese Science, GPS. É uma rede que podem consultar, gps.pt, podem consultar na internet e podem estabelecer diálogo com eles. Há mais de 2.000 cientistas registados que estão espalhados pelo mundo e convidamos 3 deles para virem falar sobre o futuro. Depois, na Madeira, é mais difícil ir, mas todas estas sessões podem ser vistas à distância também, usando as modernas tecnologias. Vamos estar com 2 cientistas portugueses, o Nuno Ferran, um deles, da Universidade do Porto. Vamos estar a falar sobre o Darwin e Madeira. Uma ilha é um laboratório de evolução e o Darwin não participou, não foi à Madeira, o barco Beagle passou ao largo, mas na origem das espécies fala várias vezes da Madeira, porque, digamos, as observações feitas na Madeira por outros naturalistas foram extremamente importantes. E David Marçal vai moderar um debate sobre a evolução e o papel da Madeira na evolução. Em Química, que é a minha universidade, a 19 de novembro, vamos falar sobre neurociência e educação, grandes avanços da neurociência, que influência é que têm nos novos métodos de aprender ou de ensinar. As duas coisas estão ligadas, ou deviam estar ligadas, e nós sabemos mais sobre o cérebro e devíamos ter resultados desses conhecimentos também na prática pedagógica. Será um psicolinguista, o Dr. José Moraes, que está na Bélgica, é português, mas está há muitos anos na Bélgica, e uma especialista portuguesa em Lisboa, Joana Rato, vão falar sobre esse assunto. Em 20 de novembro, em Lisboa, no auditório do Liceu Camões, vamos ter Matemática, a importância da matemática. É um especialista americano da Universidade de Michigan, que vem falar sobre a relevância do currículo, e teremos um representante da Sociedade Portuguesa de Matemática e outra associação de professores de matemática a discutirem as questões de uma disciplina extremamente relevante. O mês acaba em Carcavelos, na nova Business School da Universidade Nova de Lisboa, com quem hoje temos esta sessão em parceria, e vai ser sobre conhecimento e área digital. O convidado da Universidade de Virgínia é um professor Eric Hirsch, vem da área das humanidades, mas é, digamos, um dos grandes autores sobre a filosofia da educação, sobre a filosofia prática da educação. O que é que deve ser a educação nos tempos de hoje? E, portanto, temos aqui a apresentação sumária do mês. Contamos convosco para seguirem o mês. A ideia básica do mês é juntar a educação e ciência. Como veem por todos os temas que eu enunciei, são temas em que se cruzam de uma maneira mais fértil possível a ciência e a educação. Não há ciência sem educação e também não deveria... E também não há educação sem ciência. As duas estão casadas uma com a outra, e nós pretendemos, com temas modernos, contemporâneos, mostrar essa relação íntima entre ciência e educação. Nós, sem ciência, não conseguiremos, com certeza, ter futuro. Nós, sem educação, também não conseguimos ter futuro. E se as duas estiverem juntas, de certeza que teremos futuro e, digamos, temos esperança que o futuro seja melhor. Sobre a sessão de hoje, eu passo a palavra à Joana Lobo Antunes, da Universidade do ITQB, Instituto de Tecnologia e Química, da Universidade Nova de Lisboa, porque é uma parceria, e eu estou muito satisfeito com esta parceria. todos os anos temos feito uma grande conferência de ciência, associamos a outra universidade, já tivemos com a Universidade de Lisboa, já tivemos com a Universidade de Química, já tivemos com a Universidade do Porto e chegou a vez da Universidade Nova de Lisboa para discutir um tema de ciência. Temos um convidado muito especial, Peter Atkins. O professor Peter Atkins é um químico famosíssimo, com mais de 70 livros publicados, o último dos quais em português tenho eu aqui nas mãos, como surge o Universo, está lá fora. Está mesmo a sair agora, porque é a primeira vez que eu vejo este livro, e a edição deste livro é uma parceria também entre a Fundação Francisco Manuel dos Santos e a editora Gradiva, que o acolhe na coleção Ciência Aberta. Temos também outros convidados, a doutora Zita Martins, o doutor Carlos Romão, mas sobre eles falará melhor a nossa moderadora, a quem vai ficar a partir de agora entregue a sessão. Muito obrigado.
Muito boa tarde a todos. A Joana Lobo Antunes sou eu. Venho do ITQB, da Universidade Nova de Lisboa. Estamos muito contentes com esta parceria, porque o nosso assunto principal é precisamente educação e ciência. Portanto, não podíamos estar mais contentes de estar associados a este evento e a este tipo de iniciativas. O evento de hoje chama-se Pensar o Universo com os olhos da Química. E como o Carlos Filhais bem disse, o nosso convidado especial é o professor Peter Atkins. Eu não sei vocês, eu estudei farmácia na Universidade de Lisboa e para mim, até ao dia de hoje, Atkins era um livro. E a partir de hoje, Atkins passou a ser uma pessoa. E, portanto, está a ser um dia particularmente emocionante para mim. Hoje Atkins volta a ser um livro também, porque temos o novo Atkins. Durante os anos da universidade era já leste o Atkins, já compraste o Atkins, o Atkins. E portanto, voltei a ter um livro do Atkins na minha mão, novinho em folha, o que é um enorme prazer hoje. A sessão de hoje vai começar então com a conferência convidada do professor Peter Atkins, que é uma pessoa, como podem verificar. O professor Peter Atkins, como com certeza leram, mas vou só relembrar, que foi professor de Química Física na Universidade de Oxford até 2007, e para além de se ter dedicado a ensinar pessoas na sua própria universidade, dedicou-se a ensinar muitos de nós, seguramente que aqui estamos, através dos seus livros de texto, que foram precisamente cruciais para todos nós compreendermos a química física quando começámos por abordá-la de um ponto de vista académico. É um grande prazer ouvir a sua conferência hoje. E depois da conferência, seguir-se-á então comentários dos nossos outros convidados também especiais. O professor Carlos Romão, que é como eu, do Instituto de Tecnologia Química e Biológica António Xavier, da Universidade Nova de Lisboa, que é provavelmente o nome do instituto mais longo que vocês já devem ter ouvido até hoje, mas onde fazemos investigação que vai desde a química à biologia, passando pelas tecnologias e as ciências de plantas. E não só fazemos muitíssima investigação, dedicamos a ensinar e a treinar as novas gerações de químicos, biólogos, tecnólogos, cientistas de plantas. O professor Carlos Romão é professor de química, é uma das pessoas mais inspiradoras do nosso instituto e que nos relembra sempre o prazer e a elegância e a alegria que a química pode ser nas nossas vidas, e portanto é uma grande alegria tê-lo hoje aqui connosco para fazer este comentário. Também a Zita Martins. A Zita Martins é astrobióloga, é neste momento professora no Instituto Superior Técnico, antes estava no Imperial College. A Zita tem tido um percurso muito consistente na astrobiologia, que no fundo usa ferramentas da química para também estudar o universo. Portanto, pensar o universo com os olhos na química faz todo o sentido termos tanto a Zita Martins como o Carlos Romão a ajudar-nos na discussão neste tema que é extremamente complexo e que durante as próximas 2 horas vamos tentar aqui destrinçar um pouco convosco. Eu não me vou alongar muito sobre o livro está lá fora, com certeza vamos ouvir também agora a palestra e vamos dissecar muito. Mas eu neste momento já tenho felizmente o livro na minha mão, mas quando já o consegui ler antes de vocês, portanto tenho um sneak preview para partilhar convosco, A única coisa que me ocorreu depois de ter lido este livro, lembrei-me daquela famosa frase de Einstein de que Deus não joga aos dados. Passados uns anos, Stephen Hawking disse, não, Deus joga aos dados, nós não vemos para onde é que Deus manda os dados. E depois de ter lido este livro percebi que não há dados, não há jogo e não há Deus. Portanto, espero que, se isto não vos provocar suficientes perguntas para quando chegar a vossa vez de interpelarem este nosso painel, eu não sei o que mais conseguirei. Portanto, sem mais demoras, professor Peter Atkins, por favor, gostávamos de ouvir a sua palestra. Nós sentar-nos-emos daquele lado. I will now switch to English.
Okay.
Okay. We will now listen to your talk, and then we will do the comments and the discussion on the matter. Thank you very much.
Well, thank you very much. It's a great honour to be asked to contribute here this afternoon. I think it's a wonderful physical and intellectual environment, and I'm very pleased to be able to take part in the programme of events. What I'm going to try to do is to convince you, if you do not already believe it, that science is king in the sense that it provides, it's the only way that we can understand the nature of the world, that it gives us deep insight into the workings of the world. And I'm going to, of course, talk a little bit about the contents of that book, but I want to put it in a broader context. One of the things I want to sort of remind you, maybe if we could have the lights down because it's too bright, is that what science does, it does not deny the beauty of the world, but it looks under the surface of the world for the explanations in terms of the infrastructure of the world. And I think it's through that we can really get pleasure from understanding the world. And I want to talk about the possibility that science can answer the great questions, the questions that occur to all of us from the day we are born almost to the day we die. And some would claim, of course, well after that day. But I think that there are real questions, real deep questions. And there are, for example, why is there something rather than nothing? That's a real question. What's the nature of consciousness? I think, why does anything happen at all? What is the long-term future of the universe? What is the origin of the laws of nature? Which, of course, I'm going to focus on later. And what is the basis of moral behavior? These are real questions. And I think it's these real questions that science can approach with the hope of elucidation. Then, on the grey side of this picture, there are the fake questions. You know, the questions that appeal to people like Donald Trump and so on. And fake questions are really, what's the purpose of the universe? I mean, it's a fake question, really. I think it's rather wonderful that the universe, with all those galaxies just hanging there, totally without purpose. I mean, it's a complete waste of matter and energy, but wonderful. What are the features of the afterlife? Fake question, driven by anxiety. Why does God tolerate evil? It's a real problem for theologians. And all those questions, all the real questions, are basically how questions, whereas the fake questions are often, as I say here, why questions. So, for example, the set of real questions that I put up a moment ago, I phrased them in terms of why, but what I really mean is, how is it that there is something rather than nothing? What is the mechanism that drives the existence of something out of nothing? Why does anything happen? How is it that events happen? I think all the why questions that concern us should always be broken down into how questions. Then science can provide an answer. And the distinction between them, I think, is that real questions are based upon evidence. There seems to be stuff around us. So, let's explain why there is stuff here. We seem to behave in a moral way. So what is the origin of our morals? Whereas fake questions are based on no evidence. They're just based on wishful thinking. They're based on hope. They're based on human worries and the extrapolation of sort of thoughts that people have in everyday life. So this is really the distinction. Unkind people, perhaps among you, will say that real questions are the questions that science can answer, therefore science will answer them, whereas fake questions are the questions that science cannot answer, so that you insulate yourself from science. But I think really the distinction is between evidence and no evidence. An attitude of science, which I think I'm going to talk occasionally about the way that science is done, the way that science is perceived. Science is all about acorns. Acorns lying beneath the complexity that we experience in the world. And it's the job of science, in my view, to accept that the world is a very complex place, but to look for the acorn from which that complexity has sprung. And so scientists are people who go from here to here, looking for the underlying simplicity of the world. Of course, they have to reverse it as well. They have to find ways of seeing how the acorn can give rise to complexity. And that, in my view, is often a very much harder job than the reverse of looking for the simple ideas at the root of the world. But this really summarizes, in my view, the nature of the scientific endeavor. And you can see that in operation, really, because we're starting with Galileo, who really was the first of the real scientists, and an understanding of the nature of falling matter, which then Newton was able to formulate mathematically and discover simple rules that account for the behavior of particles. And even greater simplicity was achieved when Einstein came along, certainly with difficult equations, but nevertheless with the discovery of the simple underlying simplicity of the cosmos. Now, I do not deny that there is immortality in the world, but it is a very special kind of immortality. It's an immortality of legacy. So we have people like Mozart being immortal through his music, and Newton being immortal through his physics, and Tutankhamun being immortal through tourism. But that really is the limit of immortality, in my view. And one final general remark before I embark upon what I really want to say is that we can certainly go through the world enjoying its beauty in a kind of passive way. But I think understanding lights up our brains, and that we suddenly have a much richer experience if we can understand the origin of the beauty and complexity of the world. And I think what science does is taking us from a kind of passive view of the world to an active enjoyment of it. And I think this is a very important aspect of the contribution of science to human well-being, if you like. Well, those were my opening remarks, really putting into context what I want to talk about this afternoon. I want to get down to business now. And, can science, one of the great questions, which I alluded to earlier, is, can science explain how the universe came into existence? This, of course, is a scientist's history of the universe. There are kings and queens come and go, battles, wars come and go. But basically, this summarizes everything that has happened. And I'd like to presume that the universe sprang from absolutely nothing. We can talk about that in the discussion later on. So, in a sense, I can summarize one of the great questions of being is, what happened when we went from that to what we've got now? Okay. It's a question, I believe, that science, although it cannot answer it at the moment, is expected to be able to answer it as we make progress. I'm going to ask you quite often, to accept sort of payment in the future for investment now. But I think that what's a real job for science is to explain the transition from here to here. And one of the ways that science proceeds, in which this, I think, will illustrate, is that it looks to see whether the frightening question, going from absolutely nothing to what seems to be like a lot of stuff, can actually be simplified. And if it can be simplified, then maybe science has a chance of answering it. Let me say what I mean by that. If you accept that absolutely nothing was indeed absolutely nothing, then there was no electric charge. If you now look around in the current universe, you can see that I've put in positive charge and negative charge. We know that there are positive charges and we know there are negative charges. But we also know, and this is an important fact, that the amount of positive charge is exactly equal to the amount of negative charge. We know that because if there was an imbalance of electric charge, the electric force is so much stronger than the gravitational force that the universe would have blasted itself apart before it had a chance to achieve anything. So we also know that the amount of electric charge in the universe overall is zero. So in fact, although it looks as though we've got electric charge, we've got the same amount of electric charge as we had before the universe began. So not very much had to happen at the beginning of the universe. Certainly nothing had to separate into opposite electric charges. But accounting for that would seem to be a simpler job than asking where did the positive charge come from? Where did the negative charge come from? It is like going into a forest and finding a heap of soil. If there is no hole nearby, that's a difficult problem. But if there's a hole next to it, I think it's quite simple to see where the heap of soil might have come from. And it's not just electric charge. I mean, it's also angular momentum, the momentum of rotational motion. When there's absolutely nothing, then there is no angular momentum. If we now look into the universe, we find this galaxy rotating that way, this one rotating that way, this one that way, that one that way. There is zero angular momentum. There is still local angular momentum, but overall, there's no change between then and now. So we don't have to ask where the angular momentum come from. How did the universe spin up? It hasn't spun up. It's just distributed those different contributions to angular momentum. What about the energy of the universe? There's obviously a lot of energy here. Where did it all come from? That gives theologians and philosophers pause for thought. We can assess the energy of the universe. All we do is weigh it. So we weigh a galaxy, find its mass, use E equals mc squared, and therefore we know how much energy that galaxy represents. And of course, if we do it, say, for that galaxy, we'll get a certain energy. We choose another galaxy, weigh it, multiply by c squared, get more energy, add it to the first, and you can see that take that galaxy, more energy, that galaxy, more energy, that galaxy. In the end, when we've weighed the entire universe, and we know the mass of every galaxy, and we multiply it by c squared, we get an enormous energy, vast energy, energy really too big perhaps to quantify. Nevertheless, there is a big positive energy. Where does it all come from? People, theologians and philosophers anyway, throw up their hands and say, oh, must have been injected somehow, must have been generated somehow. But scientists, instead of throwing up their hands, put their hands to work and say, let's be circumspect. There actually are contributions that we have ignored here. For example, when one galaxy interacts gravitationally with another galaxy, whenever you have attraction, there is a lowering of energy. So this energy, in fact, comes down. So this energy comes down. And now you can see what's going to happen. We've certainly got that big energy. But now allow for that galaxy to attract that galaxy. Down comes the energy. That galaxy, down it comes. You can see where this is going. If you include dark matter and dark energy and so on, it looks, and this is speculation, won't disguise that fact, that this ends up down there. There is no energy in the universe. So when there was absolutely nothing, there was no energy. Now, there is no energy. Of course, it's distributed in a much more interesting way than it was here, but the net amount of energy in the universe is, in fact, probably, possibly, zero. So scientists, instead of worrying about where it comes from, don't have to worry at all. They've got a much simpler question to answer, not how did all that energy get created? They have to answer, how did it separate into these two types of opposite contribution? And that seems to me to be a simplification that will enable science in due course to account for the emergence of the universe. Now, can science explain the origin of life? Well, another major question. I mean, the crucial point here, of course, is the transition from the inorganic to the organic. How did this occur? This is really a role for chemists, archaeochemists, if you like, to resolve. No one knows yet. I mean, there's plenty of ideas. Some people think they understand how inorganic material became organic material, but it's certainly within science to account for that, and certainly within chemistry to account for that. No shortage of ideas. It's just that we do not know for sure the composition of the early Earth when the inorganic made the transition to the organic. But we can expect the answer to be forthcoming. And once you've got life, of course, then evolution takes over by natural selection. And so it's certainly the case that we can understand how the the biosphere has emerged once life has made that transition. But it's just that tricky point of going from inorganic to organic, which in due course, I'm confident, will be resolved. Can science explain how structures emerge? This is something I will talk about later on. How does some sort of random organization suddenly become a structure? After all, you could regard natural selection as a kind of elaborate way of achieving structures. Some structures would be elephants, others might be people like you and me, and so on. But somehow or other, structures emerge. I'll go on speaking. I'm going to take you back in time to the beginning of the universe, and that moment when absolutely nothing turned into something, because it's crucial to everything I want to say from now on. By absolutely nothing, I do not mean empty space. I do not mean vacuum. I mean absolutely nothing. Clear your mind of absolutely everything, and no space, no time, absolutely nothing. And absolutely nothing has three features. You might think it has no features, but in fact, in my view, it has three features. One is that it is totally uniform. Okay? Now, you can't have lumps of nothing, of denser nothing, or lumps of weak nothing. So I think before the existence of the universe, there was absolutely nothing. There we go. I want you to think of there being absolutely nothing as being totally uniform. And I want you to think of absolutely nothing as being totally isotropic, in the sense that if you take a particular point and go round it, nothing, I can't say nothing changes, nothing doesn't change, as it were, because it is uniform. And I also, by absolutely nothing, I also mean that there's no material present, there's no space, no time. So with complete uniformity. And consistent with what I said earlier on about the nature of the events that took place at the creation, I want you to think of absolutely nothing turning itself into something in a very gentle way. So the first instance of the universe will inherit all the properties of the nothing that preceded it. Now, I'm not denying that there was a Big Bang or anything like that. What I want you, because that, as soon as the universe came into existence, the Big Bang can occur and all the consequences of expanding universe and so on. But right at the very start, when absolutely nothing turned into being something, I want you to imagine and accept as a working hypothesis that nothing changed. The new world, the new universe, inherited the uniformity of absolutely nothing that preceded it. Then I need to take you to one of my heroes, in fact, a mathematical hero in this case, which is Emily Noether, who, a German mathematician basically at the beginning of the 20th century, who established a rather wonderful theorem. She established the fact that whenever you have a conservation law, and I'll talk more about conservation laws in a moment, there is an underlying symmetry. So if you can account for symmetry, then you can account for the conservation law that is associated with it. In this particular case, let me talk about the conservation of energy. Energy, as I'm sure you all know from school science and so on, is conserved. That whatever you do, the total amount of energy in the universe remains constant. At zero, as it happens, but that's incidental. It remains constant. And the conservation of energy is an enormously important law of nature because it's really the basis of causality. If you did not have the conservation of energy, more or less anything could happen. So the conservation of energy controls, it's a kind of parking warden. It controls the events that can take place. So by understanding the origin of the conservation of energy, you also understand the origin of causality, and therefore you begin to understand the origin of science. What Emmy Noether's theorem says is that the conservation of energy actually springs from the uniformity of time. So if time is uniform, like tick, 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 then according to Emmy Noether's theorem, energy is conserved. So in order to account for this major physical law, the conservation of energy, you have to account for the uniformity of time. And now maybe you can see why I presented the material about the emergence of the universe. Because if absolutely nothing, which is uniform, rolls over into being space-time, then time is uniform initially, cosmically, and therefore energy is conserved. So the conservation of energy, this great law of nature, really springs from the uniformity of time, which is inherited from the uniformity of absolutely nothing. There are other laws of conservation laws that are important as well. For example, the conservation of linear momentum, the fact that when two balls collide, the linear momentum before and after the collision is the same. Noether's theorem says that to account for the conservation of linear momentum, then you have to account for the uniformity of space on a cosmic scale. Now, once again, you can see that when absolutely nothing rolls over into being space-time, then if it inherits the uniformity of nothing, space-time, and in this case, space, becomes uniform. And therefore, you have the conservation of linear momentum. Conservation of angular momentum. Noether's theorem says that the conservation of angular momentum comes from the isotropy of space. And remember that that was one of the attributes that I applied to absolutely nothing, that absolutely nothing is isotropic. So when it rolls over into being space-time, cosmically, space-time is isotropic, and therefore angular momentum is conserved. So in this way, you can begin to see that the whole of classical physics starts to become understandable. Now, I want to extend that kind of attitude to accounting for other laws of nature. In particular, instead of thinking that the laws of nature are imposed upon us, that I believe that they spring from three activities. One is indolence, laziness. Another is anarchy. And the third is ignorance. So in this case, the inheritance of the uniformity of absolutely nothing is an example of indolence, nothing happening. What about anarchy? How can laws emerge from anarchy? Well, one of the simplest laws of nature that actually is much more powerful than it at first seems, is the fact that light travels in straight lines. More generally, light selects the path that corresponds to the least time between the initial point and the final point. There's a problem there. How does light know, before it sets out on its path, whether this particular path is going to be the shortest, take the shortest time, or should it have taken that path? Would that be shorter? How does light know in advance what will prove to be the path of least time? And I think the answer is anarchy. This is what I think happens. Light, of course, as you know, is an electromagnetic wave. Suppose you were to consider a particular path through space, and the light starts out waving along that path and ends up with a certain phase. That path has a neighbor very close to it. Light comes along that neighboring path too and waves along it. And by the time it gets to the end, its phase is completely different from the phase of the first wave. So they cancel. But consider a straight line path. Here, certainly it waves along it and arrives at a certain phase at this point. It too has many neighbors. Suppose light comes from a slightly distorted straight line. It waves along it. And the phase that it ends up with at the point, at the destination, is in fact very similar to the phase of the original wave. So they don't cancel. Now, allow every possible path so that the light travels along every conceivable path. All the curved paths have neighbors that cancel. It's only the straight line path that has neighbors that do not cancel. So if you allow light to travel through by every path between its origin and its destination, then everything washes out except the path that corresponds to a straight line. So by allowing anarchy, by allowing waves to travel by any path, a law emerges. That is, that light travels by a straight line. So anarchy works there. What about ignorance? Well, and I'll go a little bit further with anarchy of light travel motion. Think about particles. Now, an electron, when it was first identified, was thought of as a point particle. In 1927, when quantum mechanics really developed seriously, particles became waves. So what we originally thought of as a particle now has become a wave, and it has all the properties of waves. Why do electrons travel in straight lines? They travel in straight lines because of the same reason that light travels in straight lines. Particles are effectively waves that by the time that any straight line path has neighbors that do not cancel, whereas any curved path does have neighbors that cancel. So particles travel in straight lines. More generally, they travel along paths of so-called least action. So we can now understand that by allowing anarchy to prevail, scientific laws are beginning to emerge. And in particular, the laws of quantum mechanics are starting to emerge. You don't need to impose them. They actually emerge from anarchy. It may be that societies, too, are basically anarchic, but by allowing everything to happen, some societies decay, whereas some actually survive. We call it civilization. Now, there's another feature of waves which is important, that you can change if you think of a wave like that, the amplitude of the wave tells you the probability of finding a particle somewhere. Okay? That's one of the interpretations of quantum mechanics. You can change the phase of the wave. Suppose I take a wave and I shift it along a bit. The probability of finding the particle somewhere doesn't change at all, but the phase of the wave overall has changed. In this case, we say that the probability of finding a particle is globally gauge invariant. A gauge is simply a measuring rod, and a measuring rod applied to a wave. We just change the starting position of the wave. It turns out that that wave, if it is globally think of an area of space with this wave coming through it, then push the wave along. Some of it enters through one face of the region, and the rest of it leaves through the other face. Nothing has changed. And a consequence of that global gauge invariance, as it's called, is the conservation of electric charge. So you can begin to see that the foundations of electrostatics are starting to emerge. But suppose you take this wave and you squash it up a bit here, stretch it out there, squash it here, and so on. So you've changed the shape of the wave, but you have not changed its amplitude. Then still the probability of finding a particle is the same, but you have done something much more elaborate to the wave. Now, the consequence of that is that the wave no longer satisfies the Schrödinger equation, the basic equation of quantum mechanics. What you need to do is to modify the Schrödinger equation to make sure that the wave satisfies the new equation. And the amazing thing is that when the modification that you make to the Schrödinger equation is in fact equivalent to the Maxwell equations of electromagnetism. So in other words, the theory of electromagnetism emerges from what is this local gauge invariance. It's quite an amazing consequence of something remaining the same when you just decide that something is arbitrary anyway. What I do want to talk about, and I think I can find this on the slides now, is one of my favorite laws, which I shall get to when I can. The emergence of structures, how chaos can give rise, as I've got there, to structure. And this is the domain of the second law of thermodynamics. And you all know the essence of the second law. All the second law says is basically that you never see this happening. Things always get worse. So the second law states that the world gets worse. But you should be aware that it gets worse in a very interesting way. Here's a symbolism of the world getting worse. A region perhaps of compact matter or of compact energy disperses in disorder. That is what I mean by getting worse. So this is a natural tendency of decay. You don't have to think very much about the underlying reason why things get worse, things on the whole just fall apart. They tend to disperse in disorder. But suppose you've got a mechanism that can link into that decay so that this decay can somehow drive this mechanism. It may be that you can link it into another group of disorder here to build an ordered structure here. But providing overall the energy decays into disorder, locally you can actually get abatements of chaos. You can get structures emerging. So this might be a hydrocarbon fuel. When it burns, it releases the energy which disperses. It also becomes carbon dioxide and hydrogen and water molecules, which also disperse. This might be the actual internal combustion engine. This might be a pile of stones which are being driven into a structure, like a cathedral, and so on. So providing overall there is a dispersal of energy, providing overall the world is getting worse in this region, it can actually get better in some other region. Instead of bricks and stones, this might be amino acids. This might be food. This might be breakfast. This might be digestion. This might be metabolism taking part in our bodies. This could be, these amino acids are being built not this time into a cathedral, but into a protein. So we can begin to see that as we eat, so we, a structure, emerge. The second law is all about finding ways of creating structures. And we can trace it really through science back to the great disperser of energy in the sky, the sun, which, as a consequence of the fusion reaction, is dispersing energy through the solar system, being captured as it drives structures, in this case, the consequence of photosynthesis on Earth. Then the photosynthesis, the consequences of photosynthesis on Earth sort of build structures perhaps complex enough to be able to talk about the origin of matter in the universe and so on. So the second law illuminates, almost literally illuminates, the processes that take place between the sun and our ability to do science. Now, sorry, these are the slides that were not there. So imagine that I'm going back talking about them. So had I gone on a little bit, the disorder, there's anarchy, there's the propagation of light. There is anarchy again, with the cancelling paths leading to a law. There's an electron before 1927. There it is now. Once again, this is mechanics, quantum mechanics. This is gauge invariance, global gauge invariance. This is leading to the conservation of electric charge. This is a wave that satisfies the Schrödinger equation. Move it along a little bit, gauge invariance. It still satisfies the Schrödinger equation. But bunch it up in a different way, locally, close, here far apart. And the Schrödinger equation no longer applies. You have to add a little bit to it, and you get the Maxwell equations. So local gauge invariance leads to Michael Faraday, Maxwell, and the origin of electromagnetism. I don't have time to talk about Boltzmann, which is one of the most profound contributions of ignorance to understanding. But if questions come up, nor happily do I have time to talk about the origins of morality, which, once again, in questions we might emerge. But what I hope I've shown you, although I'm afraid because of that disordering of the slides, what we have started to understand is that science can trace the origins of complexity and beauty, indeed, back to very simple ideas, that we can see the emergence of this universe in very simple terms, terms that in due course we might be able to explain. And once you have got the universe, it is almost inevitable that through natural selection you get this biosphere and our ability to consider things. Well, I will stop there. I apologize for the confusion of the slides, but I hope that you have seen something of the way that I think. And I can assure you that the pages in the book are not in a disorderly way. So thank you very much.
Shall we join me, please? Yes, everything is in order in the book, so fear not. So thank you very much for the wonderful talk. We will now start with a discussion. We would like to start hearing Carlos Romão, the organometallic view of the world and of the physics and of the universe. Please, thank you very much for coming.
Well, thank you. I would like just by starting to thank the organizers for having invited me and Foundation Francisco Manuel dos Santos for this session in the presence of one of the most distinguished thinkers of science. It is indeed a really great pleasure to be here and to be able to discuss something and see this exchange of knowledge and points of view. You know, as it was already said, Professor Atkins had an outstanding planetary pedagogic career through his books. And you know, some years ago when he retired, he decided to take the prominent role of spreading the gospel of scientific reason.
When one doesn't need a job, one can
make it up.
Yes.
Okay, yes. Well done. So, because scientific reason is, I think, the one and only tool to rationally build an understanding of our universe and answer questions like the ones you pointed here, which may have meaning, right? And so I think that his position regarding to the universe has been very clear from this talk, and it's largely explained in his book that we are introducing to the Portuguese readership now today, the Conjuring the Universe. Well, I had a lot of things written here to talk. I hadn't seen the lecture of Professor Atkins, so now I have to change completely what I had here. As we have seen here, a beautiful example of entropy. The entropy in the slides resulted in an extraordinary few minutes of talking extremely complex physics in an incredibly clear way. That was a structure created after the entropy of the slides, okay? I think this is a good example. From the book, which is a physics book, really, and I had the opportunity to read what your scientific research years ago was. It was closer to physics than actually to chemistry, although it was dealing with molecules. So you really have come up with a book of physics with a tremendously acute sense of understanding and making things simple and trying to look for the really basic reasons why we are where we are, okay? And from reading this, I saw very interesting points that I had never seen because I'm not a physicist myself, and so things like what you call the in-laws, that is the really fundamental laws, most of which are the conservation laws, and I was absolutely astonished when I heard and read in the book about this Emily Noether theorem, which I don't understand yet, of course. I didn't read the theorem in itself.
It's one of the most profound theorems.
It is absolutely unbelievable. I mean, I said that, wow, this is real beauty, that a human brain thinks mathematics and comes up with an incredible explanation, or possible explanation, for the appearance of the universe.
Yes, absolutely.
I was amazed and said, is it possible that someone thinks out of nothing? You know, of course, Democritus, out of nothing, he thought about atoms.
He just invented it.
Of course he did.
So there was no evidence that Democritus
exactly. Of course.
Whereas Emily Noether's, it was a very fine piece of mathematics.
Yes, this really astonished me.
There's another minor point there, of course, that women have never contributed to thermodynamics. But
okay, they had something else to do.
Worth arguing that, but for some reason, it was done in the 19th century, when men were dominant, not like now. But Emily Noether, in fact, is a model of a female contributor to thermodynamics, because she has found the basis of the first law of thermodynamics, basically.
Yeah, exactly.
So it's a very, very important contribution.
Yes, and so I was amazed with finding a theorem like this, which explains, like you beautifully explained with your hands moving around, you know, the uniformity of space goes to the consequence of the conservation of the angular momentum or linear momentum in case, and the isotropy of space, and all these principles of nature. I have learned these principles of conservation when I was a student, and I had to go through physics lectures and so on, and they were just taught just like that. It conserves. It doesn't move. It's always the same. You can't make more. You can't get less. You know, like for instance, energy.
But there was no.
There was no explanation. You know, period. That these are principles of nature. Period. You could have written whatever afterwards. That who created these principles? Nobody asked. I mean, it was just like plain engineering.
But you see, that's the importance of retiring. Because it gives you time to think about the explanations.
Well, I didn't have to think about it. Nobody asked me, so I just got through these subjects and went to my chemistry. Okay, so. So I was very pleased also from reading your book and writing these notes here that I actually interpreted well what you meant about the nothing or the absolutely nothing turning into something which is the universe as we know it, in an extraordinarily simple way, which is this conservation. We don't know the tricks, but do you? How it?
No.
You know, you mentioned a lot of times in the book that this was done without any extraordinary thing happening.
Yes.
Yeah.
It just rolled over.
It just rolled over.
Yes. Yeah. In an earlier book, the creation, written dozens of years ago, I do try to look for the use of scientific language about how that rolling over might have taken place. But I didn't want to go into that here. But I think what this talk has perhaps done, what you're alluding to, is that it's giving you a great deal of information about absolutely nothing.
Exactly. Yes, exactly. Yeah. And if you go to philosophy, I read it somewhere some time ago, that
well, they give you absolutely nothing about it, or extraordinary amount of something.
Yeah. Actually, it is quite interesting because I read somewhere that Saint Augustine was discussing about the creation in some of his writings, and once he was asked, what is before the creation? He said, before the creation, it was absolutely nothing, and from absolutely nothing, we can't make anything.
Exactly.
And now
we discover we can.
Okay. Well, of course, he didn't have he didn't have any evidence that energy was conserved.
No.
Okay. So, well, it was good for him. Yeah, he could make it anyway. So I think that this universe inheriting the properties of nothing, is a beautiful theory. I mean, it's really very, very rewarding in a way, because you always ask the question, what was there before? We have this inquietude in our heads that we are always asking, and so nothing.
And indeed, there is still nothing. All this is nothing, but it's a very interesting form of nothing.
Yeah, exactly. Yes. So, and then you come up with these amazing concepts of looking at the interactions of matter in terms of ignorance, in terms of anarchy, and all these things. That's also very interesting, because you see things and patterns and laws of physics appearing, very simply from very simple observations. So it all makes sense, and I was very pleased to learning so much. Now I would like just to go into a little bit of chemistry, because the session is called Thinking the Universe Through the Eyes of Chemistry. The first part I had written, you just mentioned it, that is about the second law of thermodynamics. Many of the words I had here, you use them much better in the examples that you gave. How things can be created and life can be created from the second, at the cost of the second, and the activity of the second law of thermodynamics is really perfect. So I don't need to do anything like that. So I'm going to the last point, which is quantum mechanics. That, being a chemist, I had to deal a little bit with quantum mechanics, which is something that and you actually mentioned that in the book, we have no machinery in our brain to really visualize it. And this is another incredible creation of spirit and of mankind and of mathematics, that you can create a whole theory, that you make the calculations with an extremely accuracy, you find the result to the experimental result without understanding nothing of what was in the between. This is unbelievable, but it's true, and it works.
I mean, that is an absolutely crucial question about understanding the deep nature of the fabric of reality. Will we have brains that are capable of understanding the answer? And it's quantum mechanics which is beginning to show a little red light in that, because although we can do quantum mechanics, as you say, we don't understand it. And because all our experience of the way our brains have been constructed is all about watching things in farmyards and forests and things, and jungles. Our brains are built to understand classical phenomena. They're not built to understand quantum phenomena. And so the worry I have is that we won't be able to understand the final answer.
I see. Okay. Yeah.
So, who knows?
So by the final answer,
we'll be able to do it. We'll be able to predict. And explain, do the calculations.
Yes, I really understand it.
It reminds me of a remark once made about the distinction between sort of American students and British students, and it might apply to Portuguese students as well, that British students know what they're doing but can't do it, whereas American students can do it but don't understand what they're doing. And it may be that quantum mechanics is the first sign that humanity can do it but doesn't know what they're doing. Yes.
Okay, so I would just like only just to finish, if I'm allowed, to make some remarks about the power of quantum mechanics, which produces and explains the periodic table by resolving the equations of the movement and the energy of the electrons around the nuclei in the atoms, and creates this beautiful periodic table of the elements, where we can predict, and compare properties of the elements and predict their reactivity. And the predictive power of quantum mechanical calculation on molecular structures and reactivity is already leading to the rational in silico creation of new molecular entities with custom-made properties. And so my question here would be, where will this take us, chemists? So we are coming towards a situation where we don't even need the labs. You can start making the molecules and the chemistry appear in your screens of the computer, okay? Another point of view that regarding chemistry is that it took only a few decades for after Wöhler's inauguration of organic chemistry with the synthesis of urea, for chemistry to start producing alien synthetic materials, that is, materials that don't exist in nature. The molecular framework of life is a lot more complex, as you mentioned, than urea, and the picture of its beginning is still far from being understood because direct observation of the distant past is not possible. In contrast, since biology became a department of chemistry, with the Watson and Crick's discovery of the structure of DNA in 1953, the progress in revealing life's fabric has been breathtaking. Like chemistry once started to produce alien materials, the time has now arrived for biology to enter its creative pursuit, synthetic biology. Where will it lead? New biological universes, new forms of life, directed evolution of species, directed evolution of humans into superhumans. All this is possible, and it will be science-based, and therefore within the reach of wise humans. We don't need gods for creating another universe. Okay? So that was my. I have some other questions here, but we can come to that later. Okay?
Thank you. Thank you very much. Thank you. We'll now pass to Zita Martins. Please help us with the eyes of an astrobiologist, as also as a chemist, on how to think the universe and this view that we have been looking into.
Okay. Good afternoon, ladies and gentlemen. First of all, let me just say thank you very much to the Fundação Francisco Manuel dos Santos. I think it's a beautiful idea to bring people together with different views, all of us chemists, but with different views, and so I think this is beautiful. And I'd like to thank Professor Atkins for a beautiful talk, because the topic is so extremely important. And as we've seen, there are so many questions that we still need to answer through science, obviously. And so I was, as an astrobiologist, I was extremely pleased to see that in one of your slides, you mention the question of origin of life here on Earth. And it's actually what is astrobiology trying to answer, obviously. And the beauty of astrobiology is exactly that, is having different scientists from different areas, not just chemists, trying to answer how life originated here on Earth, and hypothetically, whether life exists somewhere else in our solar system and in our universe. So as a chemist, I always have a slightly different perspective of this question of origin of life than my colleagues from biology or geology or physics, etc. And so, as you mentioned really well, it's this passage that nobody knows how we move from inorganic to organic. But I'll go even further than that. I would say that it's the passage from having just molecules and minerals, so non-life, and then having life, you know? And we could go on about what is life, because even within the scientific community, there's lots of discussion of what is life, and some people discuss if a virus is life or not. So there's lots of discussion into that. I'm not going into that right now. But it's this big bridge between having just organic molecules, so the chemistry, and having actually life, so passing to biology. It's this big, big jump. And obviously there are different theories right now that try to address this question. And I would mention two of them, so you can get a little grasp of what we're doing right now in the field of astrobiology to try to answer that question of the origin of life. So theory number one would say that life originated here on Earth, but above all, the building blocks that make up life. And so when you think about life, you have to think about the basic unit of life, which is the cell. So it comes all down to the cell. How do we build a cell? if you think about the cell as a little house that you can build with Legos, the Legos will be the organic molecules. So again, it comes all down to chemistry. And so where did we get those organic molecules from? Those organic molecules that make up the basic unit of life. So again, I'll go into the theories. One of the theories says that in the bottom of the oceans, we could synthesize those organic molecules. Those are called the hydrothermal vents. And so there are scientists actually that study that. So I've passed more than a decade living in the UK, and I had colleagues actually at UCL. So I work at Imperial College, but there were colleagues at UCL actually studying that and simulating the bottom of the oceans and actually trying to synthesize the organic molecules that are fundamental to life. And they were successful. But having life, having those organic molecules, again, it's completely different than actually jumping and having life. A positive thing is that if you have the possibility to see a documentary about hydrothermal vents, is that you will see that there are forms of life. Different from the ones we have here, but there are forms of life at the bottom of the oceans because they can get the energy from those hydrothermal vents. So that also opens the possibility that in other parts of our solar system that have potentially those hydrothermal vents, that life may have originated. So that opens the door, for example, to trying to find life in the icy moons of Jupiter and Saturn. So for example, in Enceladus or Europa. So those icy moons, it is thought, because we had space missions passing by, not actually going to those icy moons, but just passing by, that there are geysers there. And so if you have geysers, there is a possibility that there is a big ocean between the ice layer. And so therefore, scientists think that there are hydrothermal vents. So all the cycle I was telling about of synthesizing organic molecules, the building blocks of life, and then hypothetically having very primitive life forms, they may exist also somewhere else. So that's theory, let's call it number one. But then there is theory number two, what it's called the exogenous delivery of the building blocks of life. That's actually what I study, and I've been studying that for the past 20 years. So what is that? So we know that the space is not empty. We've been talking about the nothing and creating things out of nothing. Well, space, we know it's not empty. There are lots of organic molecules out there. And in particular, space missions have the possibility to go to comets and asteroids. And when we don't go to comets and asteroids, we're actually visited by them. We're visited by meteorites. So any of those planetary bodies, asteroids, comets, meteorites, they're full of organic molecules that were synthesized outside of the Earth. And so Carl Schmann was talking about the extraterrestrial chemistry. In fact, that's actually what we see in meteorites. So going back again to the cell, we know which organic molecules make up the cell. So we know about the amino acids, we know about the proteins, etc. But when we go into those meteorites and actually we analyze the meteorites, what we see is that the chemistry is much more complex and much more diverse than what we see here on the Earth. And so that's important. Why? Well, again, now we have to go a little bit outside of chemistry. We have to think about geology. We know that there was heavy bombardment here on the Earth since the solar system was formed roughly 4.6 billion years ago until more or less 3.8 billion years ago. So there was heavy bombardment. All those organic molecules that are fundamental for life were being brought by comets, by asteroids, by meteorites. And so immediately after, there is the origin of life, roughly 3.5 billion years ago. So it's the perfect timing. And so even though we don't know exactly how life originated here on the planet Earth, we're getting clues. So we're getting there again. Science is extremely important to try to address this question of the origin of life. We're not there, but I'm extremely hopeful that eventually we will find and answer this question of the origin of life. And if not, well, I'm also keeping my fingers crossed to try to see if we discover if life originated somewhere else in our solar system.
Thank you. Thank you very much. We will now open for questions. Podem fazer perguntas em português ou em inglês. Temos tradução simultânea. Já temos aí? Com certeza. Vou pedir, por favor, para se levantarem e se apresentarem.
Okay, my name is João. I'm a simple citizen, so although with a background on science, but that's not why I'm here, just for curiosity. And I'd like to make a question to Professor Atkins and also thank for his contribute to mankind, which is great. And you didn't have time to cover the morality aspect, I'd like to know, but transforming it not in a what, but in a how. How is it that morality is not universal? So why is it that we don't have a universal morality like the other laws? Thank you.
Well, I think the origins of morality are discovered by looking at the evolutionary and ethological history of organisms to understand how species have survived through behaving in particular ways translates into our own codes of behavior. But not only that, I think there are two components of moral behavior. One is the infrastructure, if you like, which comes from evolution. And the other is the fact that because of our big brains, in moments of quiet, we can consider the consequences of our actions. So it's, in a way, it's a combination of the caution that comes from our ability to identify the consequences of our actions built onto our ethological background. Why aren't there? Why is there not a universal moral law? It's because it's culturally driven. That you have different cultures evolving different ways of stabilizing their society. It may be that in due course, when on Earth everything is so interconnected culturally, which we're moving towards, that a kind of universal moral law will emerge in that way.
Thank you. Mais perguntas? Any more questions? Well, if not, Carlos Ramon has plenty here in the front. Do you have the front? Please stand up.
Hi, I'm Ricardo Louro. I'm also working at ITQB. I'm an active researcher in biochemistry. And the question relates with the transition that was mentioned by you and by Zita from the inorganic to the organic. Do you really believe there is a transition, or would you accept the vision that the natural selection already is happening also at the level of geological events that somehow then lead to what we now really recognize as life, and we don't really know where to draw the line of living and non-living?
Yes, well, I think you touched on that anyway, by declining to define what is
exactly.
but because it goes to the heart of it. I mean, what do you mean by life? I mean, one definition, you'll correct me on this, is that it's a system that can reproduce itself, but not completely accurately.
Self-sustained.
Yeah, so it's not perfect replicas, but it's mistakes that lead to you and me. But I think that comes into it, doesn't it? So it's imperfect replicators. Mm-hmm. But then, to take your question further, do you need, you are arguing that organic molecules are the sine qua non of this this type of life. But you want to say that it could be the inorganic and the geological, which sort of replicate themselves imperfectly. I suppose there might be examples of that. There's types of clay and some minerals, I think, are imperfect replicators. But I think it really, you need the complexity that comes from organic molecules in order to have kind of fruitfulness in the emergence of imperfect replications.
If I may add something, I fully agree with you. And so one of the things in this origin of life field is that there are lots of people studying exactly the minerals and the roles of minerals for the origin of life. And the main role we've seen until now is to provide support actually for the first molecules to attach and then a complexity. And then there are the clays. The clays are extremely strong because it contains the water, and as life as we know it, at least here on Earth, it needs water. So the clays are so important. This twofold. It is because the clay has a structure that allows the molecules to absorb and provide the structure, but at the same time it has the water there that may have been useful for very primitive life forms. So the clays always plays a role. And I mean, we've discussed this before. If you go to Mars, 2 landing sites that have been now looking for life and has been selected are 2 that are very clay rich. So we're not just using clays to search for the origin of life here, but maybe in other places, because exactly of that, the clay is so extremely important. Thank you.
Yeah. May I ask her a question?
Well, that's highly unorthodox, so we like it a lot. Please do.
Yeah, the question is, you mentioned that the molecules of life, were formed under water.
Maybe.
Somehow. Maybe.
Maybe.
Well, I think it's very hard to happen. Mm-hmm. Because if you look at this, at the basis of the DNA, the DNA mm-hmm. basis, right? These molecules.
Yeah.
You see almost as many nitrogen atoms as carbons. Mm-hmm. This points to reactions of acetylenes or cyanides or isocyanides and stuff like that, which mm-hmm. you can find on the surface of the planet and lightning and all these other mm-hmm. conditions where there is a lot of nitrogen. Yeah. Because underwater there is not much nitrogen, really, I guess. I mean, I don't know. Yeah. So I would bet that these molecules are actually created in these storms because they look just like ready, and actually they mm-hmm. have been made this way. Yeah. Right? Haven't mm-hmm. they?
Yeah. So there is also, I agree with you, I have to say, but I had to explain all the possible theories so people don't say I'm just talking about what I do. It's exactly what you say from the chemistry point of view. But again, we're just also forgetting about the reactions in the atmosphere of the primitive Earth. So there wasn't mm-hmm. atmosphere in there. There was lots of lightning. The atmosphere existed, but not as we know it now. Different. So it was completely different because oxygen, for instance. No oxygen. It was all that it was being expelled by volcanoes. So completely different atmosphere than what we have now. And lightning was very strong. So you can simulate, and a few people have done that in the lab, trying to simulate that. So the primitive Earth atmosphere and try to see if they synthesize something. And we could go back to the Miller-Urey experiment in there. But then when you actually try to replicate the Miller-Urey experiment with the conditions now that we know that the primitive Earth had, you can't replicate the Miller-Urey experiment. So what some scientists did from San Diego was actually, and this paper was published a couple of years ago, they simulated the atmosphere that was coming out from primitive volcanoes on the primitive Earth. And actually in that case, and this was disciples from the Miller-Urey team, so Jeff Beta, etc. And so what they did was actually, they could synthesize amino acids in that case. But that's, I mean, the Earth was not all covered in volcanoes on the primitive Earth. So that's very localized. So very localized, you can synthesize those molecules. But that doesn't answer how did life originated all over the place. And that's why, in my case, I'm more in favor of studying meteorites. And you mentioned there the nucleobases. So the nucleobases, we actually have found nucleobases in meteorites. And during my PhD, what I did was actually to prove that those nucleobases in the meteorites were extraterrestrial. It was a paper that took 5 years to actually get results. And we got that. And we did that. And we got that by doing chemistry, doing the isotopes. So carbon can exist in different forms. You can have carbon 12, 13, and 14th. Let's forget about the 14th now. But the 12th and the 13th gives you where the molecule can be synthesized. So on Earth, living organisms use carbon 12, which is the lighter form of carbon. But reactions in space use preferentially carbon 13, which is the heavier form. So by doing this ratio, you can actually know where the molecule was synthesized.
But what about nitrogen isotopes as well? In taking Carlos's point, really.
Yeah.
You should also look to see whether you've got nitrogen 14 or 15 and see if it correlates.
Yeah.
Yeah. And there are people doing that.
Have people looked at nitrogen?
Nitrogen,
are they
yes.
obsessed with carbon?
No. The problem with nitrogen has to do with the mass that we need to do the isotopes. And so you would need several grams. And the problem with meteorites is that we don't have enough material sometimes. Sometimes I'm just only working with milligrams. Yeah. And so that's why we focus more about carbon than nitrogen. Yeah. But there are a few studies on nitrogen. Not as many, but there are a few studies. Yeah.
Okay, I have a few also myself. One of the things that I alluded to in the introduction, then you didn't focus that on the talk, so it would be nice for us to talk about that. Starting in chapter 1, you start saying that we have to exclude God from the way we look at it. And I am an agnostic, and I do believe that science is the most important way of looking and measuring and looking at the world. And I'm an agnostic because I have no proof other way. But what you say is that we have to really exclude it from the parts that we still don't know, because we don't know how nothing was cut in half and started the something.
But we're working towards it. And I think the expectation is that we will resolve it. And I think, in a sense, the whole purpose of science is to achieve understanding within its own perimeter. Mm-hmm. And I think that if, in the end, we discover that we must have a God in order to do the first little bit, then we might have to give in or say, well, we haven't tried hard enough. And I think it's the not having tried hard enough that I would support. You see, asserting that God did it is a kind of intellectually weak way of proceeding, because it's a very lazy way. It says it's obvious that God did it, and he did it in a mysterious way for unaccountable purposes. And we will never understand why or how. Oh, that's so distressing. And it's a kind of taking the view that we humans have brains that are so puny we will never understand until we're dead. And I think that we scientists, we humans, not just we scientists, because it's humanity that has stumbled on the scientific method. And the scientific method is evidence-based. It's a network of non-conflicting concepts, quite different from religion. I mean, when you've got one religion here, one religion there, if you've got the frontier, they clash. We see that every day in the newspapers. Science, we've got one science here, biology, physics here. At the frontier, they support each other. Mm-hmm. And it's quite extraordinary that these different springs of understanding, where they mingle, are mutually supportive. In order to understand cosmology, the science of the very big, you need to understand the science of the very small. You need to understand fundamental particle physics and so on. So to understand biology, you need to understand chemistry. To understand chemistry, you need to understand physics and so on. Everything is mutually interlocking and supportive. And this, I think, indicates that science is on the right track. And it's not just scientists who've invented their method as a kind of trades union. It's really humanity that has stumbled on this extraordinary way of discovering the nature of physical reality.
Yeah, well, that's...
Yes, I was passing the word to you.
No. So the thing is, then, it's always one of my questions, because reading the newspapers, I always get stunned with that. You know, science has been progressing. It's a creation of mankind, and it's transcultural, everything. So why is it not more widely accepted?
Because it's so hard. I mean, religion is easy to accept. God did it. Oh, yeah, I understand that. Okay, that's it. Whereas science, in order to understand, as we've been talking about, the origin of life, you see the intricacy of thought that is needed in order to arrive at a reliable conclusion. And people get bored. They want quick answers. God did it. That's right. Okay. But they don't want to have to go through with the lengthy arguments that we professionals have to try to knit together.
Yeah, but as you mentioned, science is many times is also counterintuitive, so it takes a lot of...
Oh, the whole point of science is...
I know, but that's why it's not easy for people outside science.
Yeah.
It's easier for them to say, oh, it's God, so it's so reassuring.
Yeah, yeah.
Than to actually listen to an argument and follow it.
Yeah, I think that's right. And well, science is just complicated. Yes. And then the deeper we get into understanding, the more complicated it is. And the longer the chain of argument between observation and interpretation, and longer that chain becomes, it's tough, but it's worth it.
Definitely.
But for me, there is something counterintuitive there, which I don't really understand. Because, you know, even if people are lazy enough to understand science, they know that scientists have come up with great ideas which have turned up in fantastic technological advancements for the good of everybody, right? So why don't they accept easier or more easily that some complicated subjects that are surrounding our lives on Earth can be really tackled on a scientific basis?
Well,
and they come up with all these things that you nowadays read on the newspapers, this going back to, you know, basic crazy ideas.
Yeah. Well, if you're speaking of politicians,
well, yes. Okay, for instance. Yes.
Then in the UK Parliament, I mean, there's only about a couple who've got a science degree, and the rest are just poets. And so, you know, you don't have, and of course in politics, you're really governed by populism, not by knowledge. And that's the trouble. People have got to be re-elected. People have got to say things that sound right to the electors and so on. So, you know, they're basically a bunch of liars. And it's hard to inject truth into a cage full of liars.
Yeah.
Okay.
If I may
I'm
say
not
something.
speaking of this country,
No.
where all your politicians are extremely learned.
Yeah, I think it's a question of communication, and I'm saying from us scientists and also the politicians and everything. I don't think it's just people being lazy and not believing science. It's also
No, I think there's a thirst for science.
Yeah.
And I quite agree. So, you know, people love knowing, but they've still got to have patience to listen through an argument.
Yeah, but it's also this question, I mean, because I've lived in the UK for so many years, I remember the program, The Wonders of the Solar System by Brian Cox. He's a full professor at Manchester University. And of course he was showing and giving this message about the solar system and the planets and everything. And the language was beautiful and it was so accessible. That was the most viewed TV show at one point in television. So as you say, I fully agree. There is a thirst for science and for knowledge. But if scientists also don't have the language that the people, the common people understand it, we're just talking between us scientists and not transmitting the message. And the same goes a little bit to the politicians, and I agree with you. It is a big problem when you have several ministers or secretaries of state that they don't have a background in science, so whatever we passing the message, they will smile and wave, but you know, they don't get the message and the importance. And that's what Carlos was saying. People seems sometimes that they're going back in time. This crazy idea of not getting vaccination and everything. And people just go to the internet and say, oh, I've read something. Google says that, blah, 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 and it's a lie. But why do they use it? Because the language is accessible.
But to be fair to politicians, I mean, the problems that confront them are complex. And so they don't simply have to appeal to the second law of thermodynamics or something like that. I mean, it is a multi-dimensional problem. And I think we should accept that they have a really difficult job in that respect. But if they were more rational, I would feel more comfortable.
Well, but that's exactly the importance of doing talks like we are having today and along this month and everything, so we can talk about science for everyone, including politicians. Yes, please.
Eu vou falar em português também, é mais fácil. O meu nome é Carlos Cunha, eu sou professor do ensino secundário na escola secundária, aqui no Colégio Militar em Lisboa. Começo por um comentário relativamente àquilo que o professor Carlos Romão disse. Aqui há uns tempos eu li uma definição de um cientista. É uma pessoa que explica de uma maneira que ninguém percebe um problema que ninguém sabe que tem. E eu acho que esse é o principal problema da ciência, e o professor Atkins hoje deu um contributo gigantesco para o acesso simples à ciência complicada. E eu acho que é aí o grande problema da ciência, chegar ao... Estão a ouvir?
No, I can't. This is dead.
Caiu ao chão, por isso. Foi capaz de cair ao chão.
So maybe you translate it there.
Yeah, at the end it's
okay,
easy.
let's translate.
Okay.
Bom, a primeira parte eu não vou... The second part is, can we accept that God and religion was the first basis of trying to build a kind of morality laws? And I remember that a few years ago, John Paul II visited CERN, and the journalists asked him, how could he, as God and defending creationism, was visiting CERN that was trying to explain scientifically the Big Bang. And John Paul II answered that it was a matter of a scale of time. That they were trying to explain the same things, but in different scale times. So he really didn't deny the evolution of science, and please don't be mistaken, I am a true believer of science. But I think that we can accept that God and religion is a way. It was the basis of morality in the first time, and now it's a way of people who doesn't understand, who doesn't know science, because it's too hard and it's giving too much trouble. It's a simple way to try to explain complicated things.
Yeah.
The third question is, can you oversee, can you imagine what could be the contribution, and also for Professor Zita, what could be the contribution of the thing that we now is the most amount of thinking in the universe, that is dark matter? What can you oversee that could be the contribution of dark matter for chemistry and for the evolution of life. Could it be, could it bring some explanation for that, since it's 78% of the mass of the universe? Yes? So...
Well,
Thank you.
I think dark matter is important for allowing galaxies to emerge, and for stars to live long enough to have planetary systems on which life can emerge. So it's a kind of stabilizing event gravitationally for the evolution of the universe. Without it, then maybe the galaxies would not form. And so we would just be a collection of individual stars. So everything is connected, certainly. I don't know what the Pope meant by different timescales of explanation. I mean, if he meant that religious explanations have a finite lifetime because they die in the face of emerging science, and science also has ideas that are not eternal, or seem not to be eternal, except in a few cases. I suppose there are eternal laws. I think, going back to my talk earlier, I think the conservation of energy is probably an eternal law that will never be overthrown. I suspect that the second law is also an eternal law that will never be overthrown. I don't know about other laws of nature. But I think what science is doing is trying to find eternals, and is doing it by slow but cautious, careful progress based throughout on experimental evidence. Not sure if that really gets to the heart of your question, but I think science is a construct on firm foundations. The firm foundation is observation and evidence in the public domain. And the construct on that is a network of interlocking theories, which binds it together into some comprehensible entity.
Thank you. One final question, yes, please. Aí em cima outra? Então, vamos ouvir as duas perguntas, que é para tentarmos não esticar. Por favor.
Sim, vou falar em português. O meu nome é Daniel Matias, sou da Faculdade de Ciências da Universidade de Lisboa. Estou no primeiro ano de Química, na Faculdade de Ciências da Universidade de Lisboa. E das primeiras coisas que me ensinaram e que me deitaram em cima foi a equação de Schrödinger e equações como a de Maxwell e coisas assim complicadas que, sem base nenhuma vinda do secundário, é difícil de compreender. Mas falou que ninguém consegue compreender o processo da equação de Schrödinger. E queria saber se acha que há alguma maneira de toda a gente compreender, ou se só você, sou eu e toda a humanidade neste momento, pelos vistos, que não compreende, ou que qualquer dia, alguma vez, vai haver uma compreensão total da equação. A segunda pergunta era mais para a Zita, era para saber se a questão da origem da vida vindo de um cometa, se isso não será mexer o problema da Terra para um cometa, porque quando nós estamos a falar da origem da vida na Terra, nós queremos saber como é que ela se originou, a passagem da inorgânica para a orgânica, etc. Quando nós passamos para um cometa, nós estamos a desviar o problema para como é que a vida e a origem das moléculas orgânicas e tudo isso começou no cometa também. Queria saber também isso e acho que é isso. Pronto.
Muito obrigada. Do you mind if I take the second question so
Okay.
you can answer both? Por favor.
Well, I think I can speak in Portuguese, so you have already. Por isso, o meu nome é Mónica Ribal, sou jornalista. É bastante diferente O meu nome é Mónica Ribó, sou jornalista, estudante de doutoramento em alterações climáticas. Eu tenho 3 perguntas. A primeira, qual é o... Bastante rápido. A primeira, vou tentar ser concisa. A primeira é o papel da percepção social da incerteza na ciência. Nós estamos a falar de ciência baseada em evidências. Cada vez falamos mais da incerteza, não só nas alterações climáticas, mas como em muitos outros problemas complexos que temos na sociedade e na ciência. Eu gostaria de saber como é que nós podemos falar da ciência como facto, como verdade, quando temos esta incerteza. A segunda pergunta é a construção social do conhecimento. Nós temos construção em função das perguntas que fazemos e as perguntas são construções sociais. Por isso, como é que o conhecimento é baseado em evidências e qual a sua relação com as ciências sociais? E a terceira é uma conclusão destas últimas duas, que é, nós temos o Big Bang, que é a teoria mais criacionista de todas, vai pegar na pergunta aqui que já foi criada, que dá origem às teorias evolutivas todas. Por isso, qual é o papel de Deus no Big Bang e como é que nós podemos falar de colaboração entre química, física, biologia, por aí fora, mas depois abrimos guerra à religião, sei lá, à antropologia e a todas as outras ciências que nos estudam como seres humanos. Será que nós não temos que trabalhar em equipa todos uns com os outros para perceber esta complexidade? Obrigada e parabéns pela iniciativa, que está a ser bastante interessante.
Muito obrigada. Vamos agora fechar com as respostas a este conjunto de questões. 2 pessoas que nos trouxeram questões até ver a mulher da favorita.
Gosh, yes, let me do them by 2 words at a time, I think. 2 words for each question. I think the question about understanding the Schrödinger equation and so on. I think we understand the Schrödinger equation. What we don't understand are 2 aspects of quantum mechanics. One is complementarity, that matter seems to be able to exist either as or both as particles and as waves. And the second is entanglement. That is that a state of 2 particles might persist even though there are many kilometers apart. Let's put it crudely like that. And it may be, as I touched on in the discussion earlier on, that our brains, although well adapted to understanding classical phenomena, are ill adapted to understanding quantum phenomena, and in particular those 2 very strongly non-classical phenomena. Back to the bits and pieces of your questions. I think God had nothing to do with the Big Bang. I expect he was surprised by it as we are. I think as to climate change, then I think where does truth lie? Truth lies in making measurements. Truth lies in seeking to make models of the atmosphere and the oceans that are progressively improved and are shown to be reliable in terms of making predictions and so on. So I think just like other complex phenomena, like consciousness, you achieve understanding by modeling. You don't achieve understanding by proposing a single simple equation.
Oh, yeah. So answering your question about the molecules in comets. So I didn't say that life came on a comet. That's panspermia, and I'm definitely not a fan. So what I was saying is that a theory that says that the building blocks of life, so the organic molecules, are present in comets. And we already had a few space missions going to comets, and we know that the molecules exist in there. And actually, scientists actually know how those molecules were formed. So I'm not going to spend here, we can talk later about that. That different processes occurring in our solar system, that those molecules are formed, and then they are integrating on very primitive bodies that later on will give what we call the comets and the asteroids, etc. So we're not transferring the problem, we're just, actually, we know everything since having the interstellar gases and ices until having those molecules in asteroids and comets. The basic question here, and that's the talk of Professor Atkins, is actually the big question is how do we go from having those molecules in all those planetary bodies, and yet, until today, we haven't found any life forms outside of the Earth, either in comets, in asteroids, or whatever. So again, it's not that simple as that. We simply don't go from having organic molecules, even complex ones, and then jumping to life. So that's a big question, and hopefully science will answer it. But we're just not moving around the questions. It's just to make it clear. We've been making a scientific community a long, long path until now to understand all those steps until simple complexity of organic chemistry, but we're still missing a big piece of the puzzle, that it is how did life originated.
Okay, thank you very much. I have the news that we have reached the end of our time. So I would like to thank you very much, Professor Atkins. It has been a pleasure listening to your talk and sharing your knowledge. Professor Carlos Romão and Professor Zita Martins, thank you very much for your generous comments and help in all discussion. Thank you all for coming and discussing with us. Thank you very much, Fundação Francisco Manuel dos Santos, for hosting us here tonight at the Oceanário de Lisboa. E a sessão encerrará então agora com Gonçalo Saraiva Matias, da Fundação Francisco Manuel dos Santos. Muito obrigada.
Muito obrigado. Gostaria de encerrar esta sessão agradecendo a presença de todos aqui esta noite. Em particular, gostava de agradecer aos oradores, à moderadora Joana Lobo Antunes, Professor Peter Atkins. Thank you very much for being available. A Fundação Francisco Manuel dos Santos is very proud of having you here tonight. E também os professores Carlos Romão e Zita Martins, que enriqueceram muito este debate e a apresentação que hoje aqui fizemos. Gostaria também de agradecer ao professor Carlos Fiolhais, que é o comissário do mês da Educação e da Ciência, e também à Mónica Vieira, que deu um apoio fundamental à organização deste mês da Educação e da Ciência, que é uma iniciativa da Fundação Francisco Manuel dos Santos já nos últimos anos e que é uma iniciativa, no fundo, de levar pelo país a discussão sobre a educação e a ciência. A missão da Fundação Francisco Manuel dos Santos é de contribuir para um debate esclarecido sobre a sociedade portuguesa, fornecendo informação, dados, fomentando esse debate. E nós entendemos que um dos aspectos principais desta nossa missão é, de facto, a promoção do debate sobre a educação e sobre a ciência, que são tão necessários no nosso país. E por isso, anualmente, organizamos este mês. Estamos agora no decurso dessa caminhada ao longo do mês de novembro. Iniciámo-lo precisamente em Lisboa, na Torre do Tombo, já estivemos em Viseu, vamos a Coimbra, ao Funchal, a Aveiro e depois encerramos em Lisboa novamente com um debate. E, portanto, convidamos todos os presentes, alguns já vejo que são repetentes, já os vi na Torre do Tombo e, portanto, convido-os a estarem presentes nestas nossas iniciativas, sejam as que estão fora de Lisboa como as que se realizam aqui, no fundo, ajudando-nos também a cumprir aquela que é a missão fundamental da Fundação. Muito obrigado a todos e muito boa noite. Muito obrigado.